Good morning, everyone. Thank you so much for joining us today. I hope everyone's doing well and staying safe out there. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled Measurement-Based Wellhead Fatigue JIP, Field Results and Key Learnings. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I am very happy to introduce our speaker today, Bulent Mirjan. Bulent is a principal engineer with over 10 years of engineering experience in structural analysis, subsea design, integrity management, and structural monitoring. He is based in 2H's Houston office and leads engineering projects, including our measurement-based wellhead fatigue JIP. Bulent received his PhD in civil engineering from the University of Minnesota. He is a professional engineer licensed in Texas. And he's also a part-time senior lecturer at the University of Houston, teaching structural analysis and design courses. So with that, I'm going to pass things over to Bulent to get us started today.
Thank you, Victoria, for this warm introduction. I'm excited to be here today speaking on this topic and hope you will all find the information very useful. Today, I'll be presenting the key learnings from the first phase of measurement-based wellhead fatigue JIP. But first of all, I would like to thank all the JIP participants, BP, Chevron, CNOOC, Equinor, ExxonMobil, Occidental, Petrobras, Shell, and Total. I would like to thank them for funding this project and also for their guidance and feedback. So, here is our agenda for this presentation. I will start with the objectives and then introduce the field measurements and datasets used for this study. Next, I will briefly discuss the methodology on how we calculate wellhead fatigue using sensor data and compared with predicted fatigue. And then show wave and VIV fatigue assessment results, followed by conclusions. And at the end, I will briefly talk about the phase 2 objectives. Nowadays, the drilling operations have been conducted using newer generation vessels with larger BOPs, and some of these operations take very long time in harsh environments. In many cases, our predictive models result in low fatigue life in the wellheads for these conditions. So how do we mitigate this risk? There are different ways, such as adding costly VIV separation devices, installing BOP tethering system, or using improved fatigue details. But there's another way of looking at this problem. We can ask this question ourselves. How accurate are the fatigue loads in the analysis? Can we verify them using field measurements? So therefore, there are two major objectives of this JIP. First is to provide a measurement-based foundation for drilling riser and wellhead modeling practice. And second is to ensure that the fatigue response assessment is performed with adequate but not overly conservative analysis parameters. So how do we achieve these objectives? First step is, of course, gathering the field data. This includes operational data such as top tension, internal fluid, wave height, and current speed measurements. And monitoring data includes riser and BOP motion measurements such as accelerations, angular rates, strains. Next, we generate the analysis model using as-built configuration and industry standard analysis parameters. Then we verify the conductor soil stiffness and BOP natural period using motion measurements collected in the field. Once we confirm a good match between measured and predicted BOP motions, Then we check measured and predicted fatigue results in the riser and wellhead systems. This is done for wave and VI response separately. And in the last step, if necessary, if these standard analysis parameters are not good enough, we repeat this process by changing the analysis parameters to get better match between the measured and predicted results. So please note that I need to clarify this a little bit here. Measured fatigue is not used as, is used as a shorthand for fatigue derived from measurements. So it doesn't mean that we directly measure the fatigue in the field. Okay. So wellhead fatigue is a very complex problem. It is very difficult to determine the actual physics behind it, but we can use a statistical approach to solve this problem. To do this type of study, we need to have reliable and diversified field data. Over the years, working with major operators, we collected and analyzed more than 50 years of monitoring data in total for wellhead and riser systems. So there are extensive learnings from these monitoring programs. So in this JIP, 9 major operators, like I listed at the beginning, come together and donated a total of 10 monitoring datasets. So to maintain diversity, we selected data from different regions, water depths, vessel types, soil types, and riser configurations. So in this slide, you see more details related to the selected field datasets. We labeled each dataset by region, vessel type, and water depth. For example, Gulf of Mexico drill ship 1593. So 1593 means it's the water depth. One of the key factors for the selection is the monitoring system configuration. We wanted to have data collected on the vessel, near the top of the riser, near the bottom of the riser, and on the BOP stack. Here in this table, you can see how many loggers are used in these regions of these riser stack up. There are so many wellhead fatigue drivers, as you can see in this list, but operational data or as-built riser data are well known for each campaign and hence not considered for benchmarking. So JIP focuses on soil PY curves, BOP and riser hydrodynamic parameters, current loading, structural damping, and shear 7 parameters. JIP also focuses on the parameters controlling the wellhead loading, but not resistance. So we used generic SN curves and SCF values for selected fatigue hotspots. So this is an important thing for the JIP. So we want to focus on the loading side of the fatigue problem. So we didn't want to go into the details of the resistance side. So it's part of the scope of work. So as our objective is to ensure that the fatigue response assessment is performed with adequate but not overly conservative analysis parameters, we used as a starting point typical analysis parameters for wave and VIV fatigue assessment. Here you see they are listed for your reference. For example, for wave fatigue analysis, we got these parameters from the ANVI recommended practice document E104. So we want to compare measured and predicted fatigue in the riser and wellhead for wave and VIV response. So predicted fatigue methodology is well known. We perform random wave analysis in FlexCom, in OrcaFlex, or in Abacus. But for this JIP, we use FlexCom. And for VIV fatigue, we use industry standard tool Shear 7. Advanced data analytics are implemented to determine the riser and wellhead fatigue based on logger data. Analytical transfer function method is used for wave fatigue in the riser. Mode matching method is used for riser VIV fatigue. For conductor fatigue, FE-based transfer functions are used. I don't have time to go through each method today, but if you're interested, please call or email me after this presentation so we can discuss them in detail. Okay, let's say we calculated, measured, and predicted fatigue for each data set. But we have 10 data sets, right? And for each data set, we analyze a number of motion time traces, so-called events. So they are 15 to 20 minutes long time traces. And let's say a typical drilling campaign, 2 months, 3 months. So we have data for 2 and 3 months, and each event for 15 to 20 minutes. And we have fatigue damage rate for each event. So we have a lot of data. So to quantify the comparison between analysis and measured values, we use non-weighted fatigue bias term. In this slide, you see how the non-weighted fatigue bias is calculated. With simple terms, it will tell you the conservatism for each data set. If it's greater than 1, it means that predicted fatigue is greater than measured fatigue, and so it is conservative. Okay, let's review some of the results now. Prior to fatigue calculations, we perform data screening and understand the overall riser and wellhead response. Is it wave motion driven or VIV driven in the field? So in this slide, there are some examples from data screening. Let's look at the figure on the left first. It is for North Sea semi 112 meter. We correlate riser and wellhead accelerations with measured significant wave height for the monitoring period. The horizontal axis shows the date, and the vertical axis shows accelerations. The significant wave height is shown on the secondary axis. LMRP and riser accelerations, blue and red lines respectively, are in good agreement with measured wave height, which is the pink line in the figure. Therefore, we can say that during this monitoring campaign, the riser response is wave dominant. We can also confirm this by reviewing the frequency content of the measured data. For example, on the right-hand side, you see some example plots from Gulf of Mexico drill ship 1509 meter. They show the spectral content of all the logger data. So there are data from vessel loggers near the top of the riser and near the bottom of the riser. If you look at the figure in the middle, you will see a narrow banded frequency response at 0.1 Hertz with all riser loggers except the vessel logger. Therefore, on this date or time, the riser response is dominated by VIV. However, the figure on the right shows a wide banded frequency response for the vessel and all riser loggers. So this indicates that on this date, the riser response is dominated by wave-induced motions. In the next step, we calibrate the analysis model for BOP motions using field data. First of all, we compare measured and predicted BOP displacements and angles. So if you look at the figure in the middle, the horizontal axis shows the BOP angles, while the vertical axis is for BOP displacements. Dark blue and red dots are from the field measurements, and the straight lines are from the analysis. This figure tells us how good the design soil PY model is representing the field conditions. As you can see, we had to revise the soil PY model to get a better match with the field measurements. Next, we compare measured and predicted BOP natural frequencies. If there's a difference, then we revise the soil model again to get better match. The figure on the right shows the ratio of measured to predicted BOP natural frequencies for all data sets. In the analysis, we considered API, soil PY model, John PY model, and Zachary soil PY model. But for 7 out of 10 data sets, Zachary soil model is the best fit. But I just want to highlight one thing over here, because these soil PY models are generated from the field-specific soil properties, and most of the time they are not available right at the well location. So there are some scattering in the soil properties. So yes, so we say that Zachary soil model works best in this case, but it also depends on how good your soil properties are. Now we can review wave fatigue assessment results. Here you see results from North Sea Semi 610 meter and Gulf of Mexico drill ship 1509 meter data sets. At the top, we compare the measured and predicted riser fatigue for one event only. So it's 15 minutes long time trace, or 20 minutes long time trace we have from the field, and we are predicting the fatigue response for this time trace, and also we are calculating fatigue at the sensor locations. So blue dots show the measured fatigue at the sensor locations, and red line shows predicted fatigue along the riser. Bottom two figures show the results for conductor fatigue. Two blue dots are again for measured fatigue at the two fatigue hotspots, low pressure housing weld and conductor connector weld. So we selected generic locations for the fatigue hotspots. So low pressure housing weld and the conductor connector weld are the two locations we checked in this study. In overall, measured and predicted fatigue results are comparable for these events. But again, this is just for one event for 15 minutes or 20 minutes period. So this is an important slide. It compares the measured and predicted wave fatigue results for all data sets considered in the JIP. The figure on the left is for the risers, and one on the right is for low pressure housing welds. Each color represents a data set, and each data point represents an event or fatigue for 15-minute long time trace. If a data point is above the equal line, it means predicted fatigue is conservative. If we calculate non-weighted fatigue bias, as discussed before, on average, typical design fatigue analysis is conservative by a factor of 3.6 for riser and 4.8 for Wellhead. We also compared measured and predicted VIV fatigue results. Here you see example events from two data sets, North Sea Semi 360 meter and Gulf of Mexico drill ship 1726 meter. In overall, measured and predicted fatigue results are comparable, but predicted is conservative in these examples. So similarly, we also compared measured and predicted VIV fatigue results for all data sets. The figure on the left is for riser, and one on the right is for low pressure housing weld again. Each color represents a data set, right? And each data point represents an event. we observe scattering in the data, but in overall, most of the data points are above the equal line. Based on fatigue non-weighted bias calculations, on average, typical design fatigue analysis is conservative by a factor of 6.3 for the riser and 3.1 for the wellhead. So, in conclusion, analysis results indicate that industry standard parameters for wave and VIV fatigue assessments are indeed conservative. So these are the results for the first phase. And the average wave fatigue damage bias with typical design parameters is 3.6 for the riser and 4.8 for the low pressure housing valve. The average VIV fatigue damage bias with typical design parameters is 6.3 for the riser and 3.1 for the low pressure housing valve. Riser and wellhead fatigue bias results are they scatter widely for all data sets. It's because we cannot really estimate or they calculate the actual physics behind this riser response or wellhead response. That's why it's normal to have scattering. Wave fatigue analysis can be improved by considering refined hydrodynamic coefficients on background current. VIV fatigue analysis can be improved by suppressing the excitation of slick joints near vessel and using weighted structural damping. It's recommended to evaluate the effect of wave motions on VIV fatigue and the actual probability of VIV occurrence by comparing measurements and shear 7 predictions. So these last recommendations actually brings us to the JIP phase 2 objectives. So the main objective is that the field data analyzed in phase 1 will be further utilized to explain some of the uncertainties in the analysis. I just highlighted 2 activities for phase 2 here. One is related to combined wave and VIV fatigue. The industry standard approach is to determine VIV and wave fatigue damage rates separately and add the damage rates at the end. Field data will be used to provide guidance on how to combine these VIV and wave fatigue, for wellhead fatigue. Another one is related to the actual VIV occurrence. So in the field, VIV occurs significantly less than predicted by shear 7. So VIV analysis factor of safety based on actual probability of VIV occurrence will be defined. But please note that I didn't list all the activities for phase 2 in this presentation. So if you are interested, please call or email me so I can provide more information on the phase 2 objectives. So this concludes my presentation. Thank you very much for listening.
Thank you, Bülent.
I have some questions. Yes.
Yes, we've already had quite a few come in, so I'll start asking those. And if anyone else has any other questions, you can just keep sending them to me in the Q&A box, and we'll go through as many as we can. So the first one is, what analysis parameters should be changed to get a better match between measured and predicted fatigue results?
Well, like I said, on the slide for phase 1 conclusions, the results can be improved by using enhanced hydrodynamic coefficients and background current effects. Actually, we determined enhanced analysis parameters, but I cannot really share this information in this webinar because it is paid by the JIP participants.
Okay. The next question is, can you say something about the current and wave measurements? For example, the full depth current measurement or the current directions?
Yes, so we have, for most of the data sets, we have concurrent current measurements and wave height measurements. So for current measurements, they are from ADCP, and we have both directions and the full depth profiles. Not full depth. In some cases, if it's deep water, you cannot really have the full depth, but most of the time it will cover majority of the water depth.
Okay. Next question. Did you use field-specific soil properties, and how did you model the conductor-soil interaction?
Yes, all operators supplied field-specific soil properties. Some of them are not exactly at the well location, like I said. We used nonlinear springs to define soil resistance on the conductor. Load displacement relationship for these springs are defined using different models like API, John, and Zekiri. But Zekiri model gives us a good match with field data. But as I said, we cannot really say that Zekiri model is the best at this point, as it is highly depends on the field-specific soil properties, I mean the reliability of these soil properties.
Okay, thank you. The next question is, in the dynamics analysis, do you consider some value for the static offset?
So no, we don't consider any static offset. So for wave fatigue analysis or VIV, we don't consider any offset.
Okay. The next question. How do the hydrodynamic parameters in VIV analysis compare to the default parameters in SHEAR 7?
So yeah, I cannot really share this information in detail, but what I can say is so we have using the standard parameters. The parameters we used, they are from SHEAR 7, but for some specific joints, we used different hydrodynamic coefficients to get better match with the field data. So we started with SHEAR 7 parameters, and I presented the results we get. But we changed some of these parameters, especially for specific joint types, and then we get better match with the field measurements.
Okay. The next question, how do you calculate wellhead fatigue using monitoring data?
So we install a logger at the top of the BOP and then record the motions, right? Accelerations and angular rates. From the analysis model, we define a transfer function for each fatigue hotspot in the wellhead and conductor. This transfer function correlates BOP motions with forces at the fatigue hotspot. Then we derive the wellhead stresses using field data and transfer functions. From there, we calculate fatigue using SM curve approach. So we basically use transfer function approach. Yes.
Okay. Okay. The next question, have you considered vessel motion induced VIV, the VIV in oscillatory flow?
No, we did not. So we only focus on the wave induced motions and VIV.
Next question, any thoughts on the sensitivity of the wellhead system? Is local modeling of the wellhead important? And did the wellhead suppliers collaborate in the JIP?
So that's why we did not, so it is very detailed topic. So the wellhead vendors, they did not join to the JIP. So that's why we wanted to focus on the loading side only. If we wanted to have the, if we want to look at the fatigue resistance side, then we would have participants from the wellhead and conductor vendors as well. So because of the complexity of that problem, we just wanted to focus on the loading side. Yes.
Okay. Next one is, did you observe any linear relation between the angular displacement and stresses in conductors?
Yes, so depending on the nonlinearity of the soil and also the conductor soil interaction and BOP system stiffness. In some cases, and most of the time, you see a linear relationship with angular displacements at the BOP and the conductor stresses. But you can have some cases that this relationship is nonlinear.
Okay, next question. Do you have to adjust the structural damping in the VIV analysis?
Yes, so it is one of the recommendations. We can adjust the structural damping, especially if you look at the conclusions. We say so let me see if I list it here. So yeah, so we say that the distributed structural damping should be used rather than using just one structural damping coefficient for the entire VIV analysis. It is recommended to use weighted structural damping so that for each joint or joint type you define different type of structural damping. Yes.
Okay, the next question, between the lower flex joint, the lower flex joint behavior, is it considered linear or non-linear?
Yeah, lower flex joint stiffness is considered linear. It's because we are dealing with very small motions due to fatigue. So, so the cyclic loading or the cyclic motions are mostly very small. So we consider linear flex joint stiffness.
Okay, next question. Which method was used to extract the natural frequencies from the measurement data?
So we can discuss this in detail after this presentation. You can email me, but I can just give you just a brief description. So the idea is, so you have motions in the riser, let's say at the bottom of the riser, and you have motions at the top of the BOP collected. So you will know the frequency content of the BOP, and you know the frequency content of the riser. So if you compare these two, the data coming from the BOP measurements include some kind of information for the BOP natural frequency, but the riser logger does not have that information. So by comparing these two loggers, you can identify the BOP natural frequency. There's a special method to do that. If you are interested, we can discuss that in detail after this webinar.
Okay, next question. Can we join phase 2 of the webinar, of the JIP? And if we want to, what are the requirements?
Yes, you can certainly join phase 2 of the JIP, even if you didn't join the first phase. We will get in touch with you after this webinar and give you more details on the requirements if you are interested, certainly, yes.
Great. Another question is the drill string included in the riser model and the internal flow, for example, pipe and pipe?
No, so it is not considered in the analysis.
Okay. Do you have any idea for the rotation value at the lower flex joint?
So related to drill string question, so I mean the pipe in pipe, yes, we model pipe in pipe. So we have the We have the conductor and we have the inner casings. They are modeled as pipe in pipe, but not the drill string itself. Yes, what's the next question, please?
Next question. I apologize if I've already asked this one. Have you ever observed different fatigue damage values for different realizations?
So it's not very clear to me. So yeah, maybe we need more clarification on that. Can you just please email me so we can help with that question?
Yeah, and if anyone has more questions, you can definitely continue the conversation with Bulent. You can see his details on the screen there. I think we've got time for one more. Was the damping due to the choke and kill lines considered?
So it's not specifically for choke and kill lines, but in overall, yes, we assume structural damping in the analysis model. So for wave, especially for wave-induced motions, yes, we considered structural damping, but not specifically for certain components. In overall, we define structural damping.
Okay, perfect. Well, I think that is all our questions that we had, and if we didn't get to your question, feel free to contact Bulent directly using the details provided here, and he'll be happy to give you more information on any questions and the JIP Phase 2. And thank you to our audience for your time and participation, and we hope you all found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. You can check out the 2H website for more details and to sign up. We've got a few more in the pipeline for July and August, so check out those. And please look out for a link to the recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. And thank you.
Thank you.